radioactivity. Henry Becquerel accidentally discovered this phenomenon. Radioactivity is a natural phenomenon. The spontaneous emission of radiations from an unstable nuclei. Spontaneous emission of radiations from an unstable nuclei. Radioactivity, the spontaneous emission, it's a natural phenomenon unaided by any external pressure, temperature or chemical combinations. It is purely natural and it is spontaneous. When Henry Becquerel was in the lab, he was placing some radioactive compound in a photographic plate and he could find that his photographic plate given some scintillations. Later on, Rutherford made experimental observations by taking a speck of a radioactive substance in a lead box. Okay? And he could see the scintillations on a photographic plate placed above. A photographic plate. But when an electric field is applied, he could find the scintillations in 3 places. When an electric field is applied, he could find the scintillations in 3 places. The same he observed when a magnetic field is also applied. This made Rutherford to conclude that there are 3 types of radiations which are emitted by an unstable nuclei. And he called them as alpha, beta, and gamma. The radiations which deflected towards the negative plate were called as alpha rays or alpha particles. The radiations which were deflected towards the positive plate were called as beta rays or beta particles. The radiations which were undeflected by electric and magnetic field were named as the gamma radiation. Studies revealed that alpha are stream of particles which has a mass equivalent to 4 hydrogen nuclei mass. That is, alpha particles, positively charged particles having the mass equal to the mass of a helium nucleus. Helium nucleus is positively charged, mass is equal to the mass of a helium nucleus. Alpha particles have high velocity since they are massive particles. Since these alpha particles are massive, while going through a matter, they will decrease its energy, their energy will be lost. That means these particles will have very high ionization power. The ionization power is due to its high velocity and large mass. Alpha particles are positively charged particles. They have the mass equivalent to the mass of helium nucleus. They have mass equivalent to the helium nucleus. Since they are massive and moving with high velocity, they have high ionization power, or we can say the highest ionization power among alpha, beta and gamma. Highest ionization power among the three. These are massive. Since they are massive, their penetration power is low. Penetration power, they can't penetrate through the matter to a greater distance, is low. Since they are charged particles, they are deflected by electric and magnetic fields. They can affect the photographic plate, alpha particles. Okay, stream of alpha particles we call it as alpha rays. The second characteristic radiation, that is beta particle. Beta particles are negatively charged particles. They have negative charge. Their mass is equivalent to the mass of electron. Two types of beta particles are emitted and we will discuss later. One is beta minus, second one is beta plus. Two types of beta particles, one is beta minus, the other one is beta plus. They have the mass of electron. Their speed is nearly 1/5 of the speed of light. Since the speed is very high, they have higher penetration power compared to alpha particle. Their penetration power is higher compared to alpha particle. But their ionization power is less compared to alpha particle. Mass is less. Even though velocity is high, they have higher penetration power than alpha particle. Ionization power is low. Ionization power is less. And these particles are also, since they are charged, they are deflected by electric and magnetic field, they can affect the photographic field. And the third one is the gamma radiation. These gamma radiations are undeflected by electric and magnetic field. Hence, they are stream of photons moving with a speed, that is speed equal to the speed or velocity of light, undeflected by electric and magnetic fields, moving with the speed of light. They have the highest penetration power, and have the least ionization power. So among the three, the least ionization power is for gamma rays or gamma radiation, and it has the highest penetration power. They are undeflected by electric and magnetic field, and they affect the photographic field. Okay, when this radioactivity is a phenomenon, natural phenomenon, which is shown by atoms whose mass number is greater than 205. These atoms naturally occurring nuclei spontaneously emit alpha, beta, and gamma. So as they are emitting alpha, beta from their nucleus, okay, the nucleus will transform to a new nucleus. This was studied by Soddy and Fragens, and they given the radioactive law. They told that when an alpha particle is emitted by a nucleus, for example, the nucleus is XZ. When an alpha particle is emitted, this, due to the emission of alpha particle, the atomic number of this element decreases by 2, mass number decreases by 4, and a new element is formed. This new element is known as the daughter nucleus. New nucleus is known as the daughter nucleus, and the nucleus which undergoes radioactive disintegration is the parent nucleus. The atomic number of the parent nucleus decreases by 2. Since alpha, beta, mass, that is particles which have non-mass, they are emitting from the nucleus. Okay, the number of atoms of a given radioactive element will decrease. Let us consider at a time t equal to 0. For a given radioactive sample, there are N0 atoms, or N0 nuclei. The number of nuclei is N0. Number of atoms you can take. At time t equal to 0, n equal to n0. This is the number of the nuclei at time t equal to 0. Let dn be the number of atoms decaying for a short time dt. Then dN by dt is known as rate of disintegration or disintegration rate. It is also known as decay rate. Soddy and Fagels, they told that the rate of disintegration, minus sign signifies that the number decreases proportional to the rate of disintegration proportional to the number of atoms present at that instant, that is the number of atoms which doesn't undergo decay. Those numbers which didn't take part in this radioactive decay is n. So we can say this is the number after a certain time t. After a certain time t, n equal to n. Number of atoms is n. This law is known as radiative decay law. The rate of disintegration or decay rate of a radioactive sample is directly proportional to the number of atoms present at that instant or number of atoms which doesn't undergo decay. Negative sign signifies that the number of atoms decreases. We can rearrange this equation in relation and we can write dN by dt proportional to minus n. dN by dt equal to minus constant lambda into n. Lambda is known as disintegration constant or decay constant. Disintegration constant or decay constant of that sample. Disintegration constant or decay constant. Okay. dN by dt is equal to minus lambda. Again we are rearranging this equation. Say radioactive disintegration law states that the number of atoms undergoing decay proportional to minus n. dN by dt is equal to minus lambda n. Lambda is known as the disintegration constant. Rearranging dN by n equal to minus lambda dt. Let the number of atoms at t equal to 0. Let the number of atoms at t equal to 0 is n0 and number of atoms after a time t, let it be n. So to find the number of atoms after certain time, we can integrate this equation. Here the variable is time, so I am integrating from 0 to t. Here the variable is, that is n, so I am integrating from n0 to n. Integrating, the result is integral dN by n is equal to ln n, natural logarithm, limit n0 to n is equal to lambda is a constant, integral dt equal to t, the limit is 0 and t. Rearranging ln n minus ln n0, we are substituting the limits. Substituted the limit is equal to minus lambda t. Log a minus log b is equal to log a by b. Is in the log. Log of log n by n0 is equal to n by n0. Log of minus lambda by t is equal to e raised to minus lambda t. From this, we will get the relation n equal to n0 e raised to minus lambda t. This equation gives the disintegration equation. Number of atoms after a certain time is equal to n0 e raised to minus lambda t. exponential relation for radioactive decay n equal to n0 e raised to minus lambda t. n0 is the original number of atoms of a given sample. N is the number of atoms left undecayed after t seconds. If t is equal to 1 by lambda, then n equal to n0 e raised to minus lambda into 1 by lambda. It will be equal to n equal to n0 e raised to minus 1. That is n equal to n0 by e. So we can define lambda. Lambda is the disintegration constant or decay constant. Disintegration constant or decay constant. Disintegration constant lambda is equal to the reciprocal of the time in which disintegration constant lambda is the reciprocal of the time in which number of atoms left undecayed becomes 1 by e times the original number of atoms. The number of atoms left undecayed becomes 1 by e times the number of atoms originally present. So from this exponential relation, we can give an explanation for what is disintegration constant. Now, again I am using the relation n equal to n0 e raised to minus lambda t, the exponential relation. For representing the decay of atoms, we can use a better term that is known as half-life of a radioactive substance. Half-life denoted by T half or capital T. It is the time in which the number of atoms left undecayed becomes half of the original number of atoms. Half-life of a radioactive solid is the time in which the number of atoms left undecayed n equal to half of the initial number of atoms. We can derive an expression for T half from this relation. If small t is equal to time is equal to t half, then n becomes n0 by t. So substituting in this relation, n0 by 2 is equal to n0 e raised to minus lambda t half. n0 cancels. 1 by 2 is equal to e raised to minus lambda t half, or 1 by 2 is equal to 1 by e raised to lambda t half. Then e raised to lambda t half is equal to 2 is equal to e raised to lambda t half. Taking log on both sides, ln 2 log e to the base 2 is equal to lambda t half log ln of e is equal to 1. ln of 2, 2.303 into log 2 to the base 10. Log 2 to the base 10 is equal to 0.3010 is equal to lambda t half. Multiplying this, you will get 0.693 is equal to lambda t half. So t half is equal to half-life of a radioactive substance is equal to t half is equal to 0.693 divided by lambda. disintegration constant lambda and half-life are related like this. Half-life is equal to 0.693 divided by lambda, or lambda is equal to 0.693 divided by T half. In relation, better to use this relation. Half-life period. So half-life period, determining the half-life period of a radioactive substance. This is useful in what is known as carbon dating. Generally for finding the age of process, we are using this as half-life of any radioactive, that is half-life of that radioactive. So half-life is T half, the time in which half of the number of atoms, total number of atoms left undecayed. So relation with the disintegration constant is T half is equal to 0.693 divided by lambda. Again, suppose we consider one half-life for a time t equal to one half-life, the number of atoms left undecayed is N0 by 2. For a time equal to two half-life, number of atoms left undecayed is equal to N0 by 2 into 2, half of that atoms. I am writing this as N0 1 by 2 the whole square. If t equal to 3 half, n equal to N0 by 2 into 2 into 2. So if t is equal to n half life, the total time is equal to n half life, then the number of atoms left undecayed is equal to N0 half raised to n. From this, now we are getting a relation that is t is equal to, that is n by N0 is equal to half raised to n. Okay, n by N0 is equal to half raised to n. That is n by N0 is equal to half raised to n. T equal to n t half. So n is equal to t divided by t half. That value I am substituting here. N equal to small t divided by t half. This is the disintegration time, half-life. N0 is the original number of, n is the number of atoms. Okay, after n half-life, N0 is the original number of atoms. This is one relation. That is n by N0 is equal to half raised to t by t half. Disintegration time and half-life. A better way, say, suppose we are considering a radioactive sample. If there are N0 atoms in that radioactive sample, these N0 atoms are the number of atoms when that radioactive sample was formed. That is at the time t equal to 0. Some radioactive, that is, some atoms or nuclei of this radioactive substance will have a lifetime equal to infinity. The reason, we know the exponential relation is n equal to n0 e raised to minus lambda t. So if I plot a graph with number of atoms along y-axis and disintegration time in the unit of half-life along x-axis, we see this is the number of atoms originally, then the graph is an exponential decay like this. At a time equal to t half, the number of atoms will be N0 by 2. At a time equal to 2 t half, the number of atoms will be equal to N0 by 4, so on. So, this graph will not be the x-axis, that means some atoms may have lifetime equal to infinity. Lifetime equal to infinity. And some atoms will disintegrate at the time of generation birth, that is t is equal to 0. So we can use a new term that is known as average life of a radioactive sample. Average life of a radioactive sample. Average life is represented as either T average or tau. Average life is the total life of all atoms divided by total number of atoms. Let N0 be the total number of atoms. Okay, N0 be the total number of atoms. Let us take that at any instant T, let N be the number of atoms. N be the number of atoms at any instant T. So we can write N equal to N0 e raised to minus lambda T. N0 is the original or total number of atoms at the time of birth. At any instant, n be the number of atoms, then exponential relation n equal to N0 e raised to minus lambda T. If Dn is the number of atoms, if Dn is the number of atoms which are decaying in a time interval T and T plus delta or dt. In a time interval between T and T plus delta T, let Dn be the number of atoms decaying. We can write Dn by dt is equal to lambda n. And avoiding this negative sign, we are taking the numerical value. Dn by dt is equal to lambda n. Or Dn is by dt is equal to lambda n equal to N0 e raised to minus lambda t. Dn is equal to lambda N0 e raised to minus lambda t e raised to minus lambda t into dt. Number of atoms undergoing decay in the time interval between T and T plus dt. So one can say all these Dn atoms had lived for a time equal to T. All these Dn atoms have lived for a time equal to T. I am taking the life of these Dn atoms. Life of Dn atoms is equal to T Dn is equal to T into Dn lambda N0 e raised to minus lambda t dt is equal to lambda N0 t e raised to minus lambda t dt. Lambda is integration constant, N0 original number of atoms present. Okay, original number of atoms present. Life of Dn atoms. Total life of all atoms can be obtained by integrating Dn between the limits t equal to 0 and t equal to infinity. Is equal to integral 0 to infinity lambda N0 t e raised to minus lambda t dt. We can integrate by integrating. This is lifetime of all the atoms is equal to lambda N0 taken out integral 0 to infinity t e raised to minus lambda t dt. This we have to integrate by parts. The integration is not necessary. We need only the final result is equal to lambda N0 into integral 0 to infinity t e raised to minus lambda t dt is equal to 1 by lambda square. If you are integrating by parts, so that value I am substituting here 1 by lambda square. Lambda lambda will cancel. We will get the life of all the atoms as N0 by lambda. Life of all N0 atoms. All atoms is equal to life of all atoms is equal to N0 by lambda. Then average life is equal to, representing as tau, is equal to life of all atoms divided by total number of atoms. Here, total number of atoms is N0. So tau is equal to total life of all atoms N0 by lambda. Number of atoms N0 cancels. Tau is equal to reciprocal of disintegration constant. Average life of a radioactive sample is the reciprocal of disintegration constant. Now we can relate this average life with the half-life. Half-life of a radioactive sample, just before we have derived 0.693 divided by lambda. Substituting here, average life is equal to 1 divided by 0.693 divided by lambda is equal to lambda divided by 0.693 or 1.44 lambda. 1 by 0.693. Relation between, say, T half is equal to 0.693 divided by lambda. So tau is equal to 1 by 0.693 divided by T half we can write. So this is equal to T half divided by 0.693 is equal to 1.44 T half. Let us discuss the mechanism of radioactive decay, that is alpha decay, beta decay and gamma decay. Let us first discuss alpha decay. Let XZA be a nucleus which is unstable undergoing alpha decay. During alpha decay, the atomic number of X decreases by 2, mass number decreases by 4, and we are getting a new nucleus Y. Or you can take this as X itself. ZXA is known as the parent nucleus and Z minus 2 XA minus 4 is the daughter nucleus. This is the daughter nucleus. We have here the alpha particle represented as 2He4. Alpha particle means helium nucleus which has 2 protons and 2 neutrons. If these protons and neutrons are coming as separate, a single proton, a single proton, a single neutron, a single neutron, it requires a large energy. But if they cling together to form, these 2 protons and 2 neutrons cling together to form this alpha particle, then the energy required is, that is, binding energy will be less. When an alpha particle is coming out of the nucleus X, this alpha particle will have an energy equal to, energy of alpha particle equal to 4.25 MeV. Let us see what that energy, how we are getting that energy. Q is the energy of the alpha particle, which is the difference between the parent nucleus, mass of the parent nucleus and mass of, so I take it as Y, okay, mass of Y plus mass of alpha particle. Now we have a mass defect, and this mass defect multiplied by c square, we will get energy equal to 4.25 MeV. See, actually, suppose this alpha emission is occurring in a uranium nucleus, 92, uranium 238. Then we are getting a new nucleus, thorium 90, 234 plus sulfur 2He4. So this is the daughter nucleus. Mass of uranium minus sum of mass of thorium nucleus and alpha particle. The Q value is equal to 4.25 MeV. But inside the uranium nucleus, the nucleons are having energy equal to 25 MeV. That means the nuclear boundary, if any nucleon has to escape from the nuclear boundary, it needs an energy equal to 25 MeV. But alpha particle has energy only 4.25 MeV. So how this alpha particle is coming out? This alpha particle, when it is formed inside the nucleus, it will continuously impinge on the walls of the nucleus. And if they are continuously impinging, that is exerting a compression on the walls of the container, this alpha particle undergo what is known as tunneling. So during tunneling, they didn't require an energy equal to 25 MeV. They can come out an energy which is very less, that is equal to 4.25 MeV. Alpha particle, most of the alpha particles coming out have energy of the order of 4.25 MeV. During beta decay, yet another problem is there, beta decay. Inside the nucleus there are neutrons and protons. Positively charged protons, neutral charged neutrons. How a negatively charged beta particle is coming out of the nucleus? That is one problem, that is question. Second, this beta particle coming out of the nucleus have energy which is varying from 0 to a maximum value, that is 1.12 MeV. This energy is known as endpoint energy. So the beta particles show a continuous variation of energy, whereas alpha particle, all these have same energy. Here a continuous variation. A successful explanation was given by Pauli. According to him, suppose we have a nucleus ZXA, X is the nucleus. When it is emitting a beta particle, here this is beta minus, we will get a new nucleus Y. Atomic number increases by 1, mass number remains the same. Whereas if the same nucleus is emitting a beta plus, then the daughter nucleus has mass number 1 less, atomic number 1 less, and mass number remains the same. Pauli explained that beta minus or beta plus emission is possible only if for beta minus emission from the nucleus, for beta minus emission from the nucleus, one neutron splits into a proton, an electron, and a new particle is there, it is known as anti-neutrino, which is chargeless, massless. Massless means mass is very small, represented as mu bar. Since its mass is very small, this is difficult to detect in experiments, and there is neutrinos are difficult to detect in experiments because their mass is very small. They can penetrate through the matter, to a greater distance because of its very less mass. So, for beta minus decay, a neutron converts to a proton, then an electron and an anti-neutron. Proton resides inside the nucleus, so mass number will not change. Electron and neutron are coming out of the nucleus. If this electron carries maximum energy, then energy of neutrino is less. If this electron has less energy, then neutrino will have high energy. So the energy is shared between this. Then we can explain that energy distribution, continuous energy, variation in the energy. So when beta minus emission, a neutron in the nucleus converts to a proton, then a beta particle, beta minus, this is beta minus, and an anti-neutron. Whereas in the case of beta plus emission, here the atomic number decreases by 1, and we are getting E0 plus 1. This is beta plus. It is known as positron. Say Z minus 1 plus 1 is equal to Z. Atomic number C. A, mass number C. Here, mass of positron is approximately 0 we have. Along with this positron, one more particle that is known as neutrino is also emitted, chargeless massless particle. So this is the explanation for beta plus. Inside the nucleus, a proton. Outside the nucleus, a proton will not dissociate into a neutron and a positron. Here, inside the nucleus, a proton converts to a neutron, which is chargeless, plus positron plus neutrino. This is neutrino. So this is the explanation given by Pauli. For beta minus decay, a neutron is converting to a proton, then a beta minus and an anti-neutrino. For beta plus, a proton inside the nucleus converts to a neutron, a positron, and a neutrino. Energy is shared between these two. The atomic number. When beta plus emission takes place, the daughter nucleus will have atomic number 1 less compared with the parent nucleus. Okay, the energy is shared between, in beta plus emission, energy is shared between positron and neutrino. In beta minus emission, shared between electron and antineutrino. Now we come to gamma decay. Gamma, electromagnetic radiation. Gamma is electromagnetic radiation. Whenever a nucleus X emits an alpha or beta, either alpha or beta, this nucleus, that is the new nucleus, will be the, I represent it as one. New nucleus, it may be having atomic number Z minus 2 if it is alpha emission, A minus 4, that is a mass number. This new nucleus will be in the excited state. The star represents excited state. So since this nucleus is in the excited state, it will emit one or more gamma radiations and come to the final state. So since the nuclei after emission of alpha or beta, since they are in the excited state, after emission of one or more gamma radiations, these will transit to the stable state. For example, let us consider a nucleus, cobalt nucleus. This is cobalt nucleus, 27C060, cobalt nucleus. It emits a beta minus, and now we are getting beta minus emission means atomic number increases by 1. We are getting nickel, mass number remains the same, isopass. Okay, this is in an excited state. It will emit a gamma radiation of energy equal to 1.17 MeV and comes to another excited state. This is also excited, but its energy is less. Okay, energy is less. Then it will again emit a gamma radiation. Here emit a gamma radiation of energy 1.33 MeV and comes to the stable state. In the stable state, energy of nickel, that is nickel, is equal to 0 MeV. Now this is in the stable state. Here no star mark is there. So this nickel will have an energy equal to 1.33 MeV. This is the energy state. And here, the first, that is, after the emission of beta, the nucleus formed is, that is, excited. This will have an energy equal to 1.33 plus 1.17 equal to 2.5 MeV. So these are the excited states. These excited states emits two gamma radiations. Okay? Because here we have two excited states. If only one excited state is there, only one gamma radiation is there. This is the theory behind gamma decay. So the emission of beta or alpha will make the nucleus in the excited form. Then they will emit gamma radiations and come to the stable state. Okay?